very much for the introduction and also for the invitation to provide one of these COMET webinars. I'm going to, if you don't mind, stop my video. My Wi-Fi signal is not particularly strong here, so you won't see me again for some time. But I'm going to start sharing my screen with you, where I have my presentation. Okay, so I trust that everyone can see this okay. The presentation is entitled Earthquakes of the Silk Road, reinterpreting the historic and prehistoric ruptures of Central Asia. I've given a title of Field Trips, and this is Kyrgyzstan. And the theme that is of the insights that can be gained by combining both satellite imagery, remote sensing, and also field work, right? So we're going to have those two elements running throughout. I also want to say that this presentation may be given by me, but the work that I'm presenting is really the results of many years of work and by many people. In particular, I would like to give thanks in advance to a number of my PhD students over the past years, and it really is their work that I will be presenting. So Grace Campbell, Nicholas Dodds, Tim Middleton, Chi Yu, Wendy Tsai, Roberta Wilkinson, and Joe Yu. Also, there have been a number of postdocs associated with the projects and associated with COMET, Austin Elliott, Christoph Grötzner, Magali Rizza, all of whom have now gone on to jobs elsewhere and continue to be active in this kind of research. With any talk such as this, I should also thank the various funders who have obviously COMET, who has been, the work has been part of COMET throughout. A number of UK Research Council projects. A lot of what I will show has come within the Earthquakes Without Frontiers program, which ran from 2011 to 2017. The Looking into the Continents from Space program, also as a university research fellow for a number of years. Presently, we are funded through programs by the Liebig Trust and also through the Science for Peace and Security program of NATO. And we've obtained satellite imagery from a number of sources. I will show in this talk ones that we have obtained through the Digital Globe Foundation. So we defined this as earthquakes of the Silk Road. Why did we do that? Well, the Silk Road originating over here in central China, the city of Xi'an, stretching through to the shores of the Mediterranean in the west, and with a number of trade routes that go through the interior of Asia. And you see in this map, right, that wherever you have these mountainous regions within the interior of Asia, you also have earthquakes. Earthquakes here represented by the red dots. These earthquakes are caused by, at a plate tectonic scale, the motions of the continents of Africa, Arabia, and India, all of which are moving northwards at various rates, millimeters to centimeters, with respect to some stable Eurasia, somewhere up in the north. And the problem that we have throughout this zone is that we have many earthquakes spread on many faults. We don't have a single fault line dividing these continental regions. Then these faults are spread over wide regions. And just to get that across to you, here in India, we have a zone about 3,000 kilometers in north-south extent, right, in which earthquakes are occurring that are due to this continental collision between India and Eurasia. This causes a widespread hazard. Right? These constitute hazard for populations in these areas, but in any one place, there can be a gap of many thousands of years between earthquakes. Right? And so throughout, my own approach has been to try and understand the earthquake record by looking over an appropriately long time period that we can start to examine the record of earthquakes in any one particular place. And that means that we need to look over periods of hundreds, thousands, sometimes even tens of thousands of years. In order to achieve this, what we end up doing is to bring together modern measurements. Right? Wherever there have been recent earthquakes, we can use techniques such as seismology, satellite measurements, etc., with data that we take from historic records, prehistory, and especially the expression of earthquakes in the landscape, and geological data. Right? So we're trying to fuse all of these things together. We mentioned hazard. If we are looking in terms of a societal aim within our work, we see that the interior of Asia has suffered from multiple large earthquake disasters in recent decades. Right here, this is a picture, I think, by John Elliott that was produced some years ago. Magnitude scale, the earthquakes go from blue, green, yellow to red in terms of increasing magnitude. The size of the circles represent disasters in numbers of deaths, 10,000, 50,000, 100,000, and 250,000. And you see many such events within the interior of Asia, in China, in places like Iran, etc. One example from Iran, the capital city of Tehran, actually exemplifies what we are talking about here. The city of Tehran, right, you can see the street plan of a part of the modern day city of Tehran. Right, it extends beyond the limits of this perspective view. And there are a number of active faults. Right? There's one that defines the edge of the basin, the North Tehran is growing, a fault-related fold that is growing within the interior of the basin. Scale 10 kilometers. This is a megacity, population 10, 15 million at the present. There have been earthquakes that have affected Tehran in 855 AD, 958, 1177, and 1830. Right, so the long historic record in Iran helps us to interpret the geology, and the geology can help us to extend the short historic record in other regions. Right, so i.e. in Iran, we can help to interpret the geology, the landscape, using the history as a guide, and then after taking those lessons, after learning what to look for, we can export them elsewhere. But there's also, Tehran gives us a sense of the urgency behind this problem, right? Because this is Tehran at the present day, or even a part of Tehran, as I said. This is the size of Tehran in 1947. So we've increased by an order of magnitude in terms of size, an order of magnitude in terms of the population. Tehran in 1947 was a relatively smallish town. It was sited in, the siting is no accident. It's got mountains to one side. These mountains provide a source of water that can sustain these populations. And throughout the inner parts of Asia, we see a repeated story that population centers have been built in close proximity to active faults. These are the habitable areas, and if we move away from the active faults, we have less availability of living space, either for agriculture, for water, etc. And just to reiterate that one of our aims throughout has been to try and examine the active faulting and the earthquake hazard in urban regions. This was a paper by a colleague of ours in the Geological Survey of Iran, Mortaza Talabian, a paper that was published in 2016 with a number of COMET co-authors, where we're trying to examine those active faults within Tehran itself. A better understanding of those faults obviously will eventually, hopefully, lead into a better appreciation of the risks and into mitigation efforts. We can also use Central Asia as a natural laboratory. And why is that? To learn a little bit more about earthquakes in general. And the first thing is, reason that we might want to look at Central Asia is that large intraplate earthquakes are rare. We actually have a very limited database of examples that we can draw on if we want to understand the variability of earthquake rupture. There's something else in Central Asia, and that's that there is actually an extraordinarily rich record of large earthquakes that occurred in the early to mid 20th century, might even go back a little bit, late 19th century through to mid 20th century, which constitute a very important data set of rupture in large magnitude earthquakes, right? So we can take these examples and we can increase our case studies that help us to examine some of the general processes that might period is actually a very important one, because we can combine, or we can treat these earthquakes as modern, right? We can combine remote sensing, field investigation, seismology using early seismometry readings, heritage remote sensing imagery, aerial photos, etc. And we can view them both in a modern sense, but we can also view them historically, right? We can use them to help us bridge that gap and to go further back and to examine the historical palaeoseismic record and to actually understand what kind of earthquakes we would be dealing with when we go further back in time. So these are critically important for us. But why Central Asia? Well, another reason is that the landscape is such that we retain evidence of single event ruptures spanning for greater than 1,000 years. We can generate a data set covering a sufficiently long period to capture the variability of rupture in continental interior settings, historic and prehistoric events. Treating that final point, right? Just as one example, this is from Mongolia, from central Mongolia. So here we have a satellite image. This is actually a COMET satellite image, 1 meter resolution. You can see ruptures, right, from an earthquake running through this landscape here, from a normal faulting earthquake. We can map these in some detail. We can really get at what was occurring in terms of sense of slip, etc. We can go into the field, we can easily observe these earthquake ruptures, and we can measure the amount of displacement that occurred on those scarps. What's remarkable here is that this earthquake, which involved about 4 meters of vertical displacement, has been preserved for over 4,000 years. I mean, it's still very fresh. It's still easily available. You know, we can actually go out and map this earthquake as though it is one that happened in the recent past. We have that level of detail. But for much of the talk, we're interested in earthquakes that have occurred in history and in the early instrumental period. If we start in the east, we will look at Xi'an. And in Xi'an, there was badly damaged by the 1556 Huashan earthquake, which caused over 800,000 casualties. It remains the most destructive earthquake in terms of loss and life within history. And it has an often quoted magnitude somewhere between 8.25 and 8.5, an extremely large earthquake. The 1556 earthquake, Huashan, occurred down here. It is one of a series of earthquakes that have occurred around the Ordos region of central China. And a number of these have been recorded as magnitude 8 or greater, right? So including the Huashan earthquake, 1556, the 1303 Hongdong earthquake, the 1739 Yinchuan. These earthquakes give us a chance to calibrate the historical record in China, in central China. They also give us implications for understanding the present day hazard. Obviously, there are large populations all the way around here with relatively few earthquakes that have occurred in recent decades. The work that I'll present here was mainly done by Tim Middleton, Joe Yu, PhD students in Oxford, and a lot of the work is actually the focus of the Earthquakes Without Frontiers program, and then after that the STINGS program, which was increasing resilience to natural hazards in China. Here is the Huashan epicentral region. The city of Xi'an is just off to the edge. These are intensities, isoseismal intensity values from going up to 11 right in the middle and outwards. And if we zoom in a little bit, the city of Xi'an is roughly here. This is the valley of a major river. We have a smaller city, Weinan, here, and for a long time, scarps have been recognized along these two faults, the Huashan and Weinan faults, combining to a total length of about 90 kilometers. And these scarps have been interpreted to be the source of the 1556 earthquake. What we have done in our study, or Joe Yu did in his study, was to take stereo Pleiades satellite data to produce a very detailed digital elevation model and to examine those scarps and the geomorphology, the landscape associated with them in some detail, to really interpret them properly. Was this the source of the earthquake? Is it likely it was the source of the earthquake? What actually happened in the earthquake? How much slip was there, etc. Right? Here is a perspective view looking south. The fault runs along the base here. Right, you have what is called the Weinan tableland on the upterrain side, a number of large landslides which were formed during that earthquake. And if we zoom in here, where there is a small river catchment, the Qishui River, it flows across the fault. And when we look at that in detail, we can see where the fault goes. It goes between these white arrows. There is a scarp here, right, in this alluvial terrace. There is no scarp here in this middle part, what we call T0, the youngest terrace. And there is a scarp here where immediately below the village of Qishui, which is below this T1 terrace, right? And the scarps are at different heights. So a lower scarp, no scarp, a higher scarp. We can also view this digital elevation data in map view. It helps us to, this is the same view. This is the village of Qishui. These are the scarps that we were looking at before. The fault runs along the edge of the tableland, and you can get a sense that there is indeed a scarp running along the base here. And we can zoom in even more detail and into this side, this boxed area. And we can make a nice interpretation of the landscape. We see a river, the Qishui River, which has an alluvial terrace associated with it, which post-dates the last motion on the fault. There is no scarp visible in this T0 surface. T1, an older river level, right? So representing some time before the river downcutted, has a scarp which is somewhat higher, and then there is also a higher terrace as well, T2. We can take profiles, right? So here, profile E3, which is taken through the T1 terrace, gives a height of about 7.5 meters. Through the T2 surface, it's more like 15 meters or so. Okay, so these are the kind of numbers we're seeing. Just after the digital elevation, the satellite image was acquired, a quarry here was extended across the fault, enabling us to get a cross section through that. And in the walls of that quarry, just as we're crossing the fault, we could actually see a cross section of the fault. Here it is, and here is an interpretation below of what we are seeing in the walls. There's a lot of detail in there, and actually this is something that is still controversial. There is one earthquake, at least, represented in here, but there could be multiple, right? We don't know for sure, and this is actually something that I think will remain a mystery from this one exposure that we have available to us. But we have at least one earthquake. And from dating that we were able to do here, we can see that that earthquake occurred within the last 1,000 years. We have some radiocarbon age from these layers here, which give about 900 years before present. So we know that this is this fault has broken within the last 900 years, apparently with a large amount of slip. If this is a single earthquake, then the slip here is about 10 meters. In order to have created the offset in some of these units on the footwall and hanging wall. So a very large tender here is the 1556 earthquake. On the right hand side, I just show a scenario in which we can build the observations in the quarry wall from a single offset. Of course, as I say, it does not preclude that there were that this is formed from more than one earthquake. These scarps are found along about a 90-kilometer length along these two faults. So the scarp is about 90 kilometers long with a seismogenic thickness of about 20 kilometers. The slip reaches 10 meters. If that was a single earthquake, this suggests a magnitude MW of somewhere between 7.8 and 8.0. Still a very large earthquake, but is much smaller than stated in the catalogues. It's much smaller than an 8.5 earthquake. This is not a one-off, right? We have also seen, we went to look at the Tien Shan earthquake, 1739, and this is often stated to be a magnitude 8 earthquake. When we go into the field, we look at the length of the fault break. It's about 90 kilometers. We measure the throw, 3 to 5 meters. We can estimate a moment magnitude somewhere in the range 7.1 to 7.6, much smaller than is often reported. And here you can see the scarp still very well preserved. The actual offset, the vertical offset here is from this part of the land surface here down to this level here. Okay, this is post-earthquake deposition. In some places you see the scarp superimposed on higher scarps, right? So this is actually the free face from the 1739 earthquake, and it's superimposed on a much larger scarp, multiple earthquakes. And in fact, here, this is quite a famous place. The earthquake ruptured and displaced vertically the Great Wall of China, right? So you see that these do not align, right? So there seems to be some vertical displacement. However, there is some debate here because this has been heavily restored as to exactly how firm any measurements can be made in this one side. It was fascinating nonetheless. And this is why, in order to try and understand why this might be, this is why the early 20th century earthquakes, early instrumental earthquakes, become so important. There was a very large earthquake in 1920 in central China. Here is the Ordos region that we were talking about before, right? So Xi'an is just down here somewhere. And this is the rupture from that earthquake in 1920. Killed upwards of 200,000 people. And this earthquake can present or can provide for us a bridge between the modern and the historic periods. So it's an earthquake that we can study both in the sense of it being a modern earthquake and a historical event. This is the work that was done mainly by Chi Yu, another PhD student in Oxford. And this is a paper that has just been published in the Journal of Geophysical Research. I recommend that you all go and look at this paper. It's a really nice piece of work. And it represents an enormous amount of work that has been done by Chi. First of all, she had to collect, digitize these early analog readings, right, of the earthquake. She then had to convert them, get rid of these curvatures, etc., which are all these artifacts of the recording process within these early seismometers. She had to work hard to get a good coverage in terms of azimuth around the earthquake source, and from that she was able to determine epicenter, magnitude, an estimate of moment magnitude here giving 7.9 plus or minus 0.2, and also some sense of the focal mechanism, right, which is looking really like this predominantly strike slip mechanism, but quite insensitive to depth. And notice this magnitude that she gets here, moment magnitude. This is quite a lot smaller than some of the stated magnitudes for this earthquake, which range anywhere between magnitude 7.8 and 8.7. So we're looking at the smaller end of that in the measurements that she has made. See in the landscape from that earthquake. Here is the rupture. This is a digital elevation model. Right here is the rupture. You can see offsets of features. This feature here, this wall here, right? And you can measure the amounts by which they're offset, 4 or 5 meters, etc. And over the 3 segments of the rupture, she finds average slip of 3 meters, 4.5 meters, 3.5 meters. Again, these kind of numbers lead to an estimate of moment magnitude somewhere between 7.7 and 7.9. So in agreement with what you get from seismology, right? So there seems to be a reasonable agreement there. The question is, why is this so much smaller than some of the things we see in the literature? And well, I mean, this is kind of what she came up with, is that it appears as though a lot of the very large magnitudes that we see for these early earthquakes are using a surface wave magnitude scale from Gutenberg and Richter. It seems that the intensity magnitude relationships built for historical earthquakes use that same scale. And there's a potential that these are actually systematically overestimating the historical magnitudes. She comes up with a possible solution to convert into something that will approximate more what the moment magnitude would be. And so there's a lesson here, right, is to know which magnitude scale you're using, and to be very clear on that and the implications of that, right? And I think there's obviously a lot of follow-up work that can be done from this study of the Haiwan earthquake. Moving further west into the Central Asian republics, parts of what were the Soviet Union for many decades, and throughout a lot of the time that we will be that a lot of these earthquakes occurred in. I think we have an amazing sequence, well, not sequence, but a database of large magnitude earthquakes. If we go to earthquake 1889, Kamin earthquake 1911, all of these other ones going through Tajikistan, another big series, 1907, 1911, 1949. In Turkmenistan, we have the 1895, 1928, 1948 earthquakes in Ashgabat. And actually, these earthquakes here really form the basis of Leverhulme Trust project that we have to try and better understand the earthquakes that have occurred from their ruptures. It also is the focus of a lot of people within our team in Oxford, Ben Johnson, Tamara King, Neil Marshall, Ian Pearce, Wayne Tsai, and Roberta Wilkinson. And what we're trying to get at from these is to examine some of these very complex multifault ruptures, also clustering in space and time, which seems to be apparent from this map view that I show you here, where using in these areas, there's typically a short historic record, but a long residence time in the landscape, so we can use what we learn to go further back in time, get a better appreciation of earthquakes in these regions. And finally, we are also, I think, in these areas, we're uncovering some evidence of extremely large earthquakes. And so it gives us the opportunity to really probe the upper end of the intraplate magnitude scale in at least a few of these examples. Not the ones that I'll show you, but some that we're working on at the present. If we look at the city of Almaty, a case study, Almaty is just here, just underneath these stars that say 1911 came in. Here's the city of Almaty at the foot of the northern Tien Shan, the Zailiski range of the Tien Shan. And on a map view, here's Almaty, Misilkul, right, and the Tien Shan Mountains. Here we have earthquakes from a compilation by Al Sloan and others in 2011. The images that I'm going to show you are from Grace Campbell. The focal mechanisms have been divided by depth. So yellow being ones at 15 to 30 kilometers and red ones being greater than 30 kilometers. So we see the potential for very deep earthquake sources, especially on the edges of the Tien Shan mountain ranges, which may mean that for any given fault length, we may have greater fault areas, therefore the potential for greater magnitudes of earthquakes. The city of Almaty has not really experienced much in the way of earthquakes in recent decades, and yet if we go back into history, we see that Almaty was badly damaged in 1887, 1889 by Chile by the Chile earthquake, quite distant, but a very large source apparently, and 1911 Chongqing earthquakes. The source of the 1911 Chongqing earthquake is actually quite well known. It was mapped immediately afterwards in this monograph, with the results of which were put together in a monograph by Bogdanovich, published in 1914. And have been re-examined since. They're still very good, fresh and easy to see at the present day. Seismology gives a moment magnitude about 8, and field mapping, and both from the original surveys and from later ones by Delvaux et al., Arrowsmith et al., give lengths of anywhere between about 150 to 200 kilometers, 3 to 4 meters of average slip with potential magnitude maximum up to 14 meters, and a moment magnitude in the high magnitude 7s, right? So roughly equivalent. The 1889 earthquake, however, is not very well known. We know from intensity measurements, right? So levels of shaking, which were done by questionnaire after the earthquake in 1889, that there seems to have been a much wider pattern of damage than from the 1911 earthquake. You see these much wider extent of these isoseismals, potentially a large magnitude, deep rupture has been inferred. Seismology, and this is really small number of data available, appears to support a magnitude of 8+. And from our work, one thing that we've been doing is to try and map out fresh ruptures in the epicentral zone, which suggest about 175 kilometers of rupture in 3 segments involving both left and right lateral slip. Seems to be very complicated, with a large slip to length ratio and individual short faults, right? So I think this holds a lot of lessons for some of the recent multi-fault earthquakes that we've been seeing, such as those in New Zealand, etc. This is what it looks like in the field, right? One of those fault segments, 35 kilometers in length with a slip of 10 meters and little geomorphic evidence of prior slip. You can see some in the long-term geology, right? This is a fault scarp over here, right? The fault runs along the bottom, but everywhere else in the landscape, there is only that one earthquake. We can look at this using palaeoseismology. Here is a trench dug across the scarp here. We find that there was only one earthquake represented in the last 6,000 years. And we see that same single earthquake in a older terrace. We don't know how old up here. So potentially a recurrence time of at least 6,000 years, potentially a lot longer. And so through those studies, we're actually trying to piece together what seem to be very large earthquakes with sources that are very complicated, right? Involving a number of individual fault segments that have failed simultaneously to provide large magnitude sources, and that have in some ways very unusual sources as well, with these components of both left lateral, right lateral, etc. One thing that has been noted is that here is the city of Almaty, which has been heavily damaged in the past by these earthquake sources. 1911 south of it here, 1889 to the east of it here, that Almaty actually sits on a thrust fault which defines the edge of the Zaliski mountain range, and there is no historical record of earthquakes on that fault itself, right? The historical earthquakes all seem to have been elsewhere. damage caused by these more distant sources. One thing that we're actually trying to do here, and this is work by Roberta Wilkinson plus our colleagues in Kazakhstan and Kyrgyzstan, is to examine what that fault is capable of doing using paleoseismology. So we dug a trench here across the main fault in this segment, and we've uncovered evidence of prehistoric earthquake ruptures. And this is work that will, she's putting those results together as we speak, and hopefully we will get a better idea of years. Also within the Tien Shan, we've been going further back in time to look at individual earthquake ruptures, right? We can still identify the individual earthquake ruptures from those historic ones, right? Chilik, for instance, here. But we can look at prehistoric ones. There's one just nearby to Chilik, the Bartagai rupture, and one really dramatic one, which is the Lepsi rupture up close to the steppelands, the Kazakh steppe. This is what it looks like at its close to its eastern end. It's really dramatic, really fresh still. And just to say with this one that from the available dating that we have, it appears as though this earthquake occurred within the last 400 years, right? So this is something that has not really got into the earthquake record, into the historical record, even over those time periods. It appears as though it was very large. It involves slip of way over 10 meters in places. And actually, it may have been part of a much larger rupture that continues here onto this Dzhungarian fault and may have been several hundred kilometers in length. And this is the work that Wendy Tsai is doing, is trying to follow this up at the moment as part of her PhD research. Leaving the Tien Shan and going further west, we're heading to the Arabia-Eurasia collision, and we're looking at Iran and the countries bordering the South Caspian Basin. Here we have had, in recent decades, regular occurrence of destructive earthquakes, magnitudes typically between 6.5 to 7.5. But also we have a very long historical record. And in this map on the left-hand side, a compilation by James Jackson that he did in 2007, we can see the white dots are those that have occurred in instrumental times. The red dots are those that are taken from historical records, which stretch back hundreds, if not thousands of years in some parts of Iran. And you'll notice that there are some prominent gaps. For instance, here, the edge of the COMET Mountain along this active range front, which we wonder whether this is to do with an actual gap, a seismic gap, a fault that has not ruptured over the last few thousands of years, or whether it's actually a gap in the historical record, right? Do we see recent earthquakes and they're just perhaps not all getting written down over that time period? Just on the right-hand side for completeness, these are earthquakes that have caused large amounts of casualties, 10,000 deaths per earthquake in white, over 30,000 deaths in red. The city of Ashgabat, the capital city of Turkmenistan, was destroyed in 1948 by a very large, an earthquake. Excuse me. But the main part of that range front has not sustained an earthquake in his. If we look at quite limited numbers of information on earthquakes. Of course, we had the Ashgabat earthquake in 1948. This is well documented to have caused extreme amounts of damage to the city of Ashgabat. Just on this zoom in here, this is the city of Ashgabat here. And it appears as though the source of that earthquake was somewhere to the southeast, potentially associated with thrust faulting beneath this geological fold here, right? That seems to be the most likely option. One of my PhD students, Neil Marshall, is currently trying to improve or put together all available knowledge on that earthquake and also to do additional mapping. Near Ashgabat, we also have earthquakes potentially from archaeological records at Nisa. This is the city of Nisa, Parthian city on the outskirts of Ashgabat in 200 BC, and also in 2000 BC at the Bronze Age city of Aktepe. We also have a number of earthquakes in the Caspian lowlands, Balkan and Bat-Kumdag regions, 1895, 1946, 1983, 1984, and 2000. These are all out here, right? Everywhere in between, we do not have any records of significant large earthquakes. And I have a raised hand, but I don't know how to look at the chat right now. Maybe I could wait to answer your question, because I've almost finished the talk, and we could have the questions at the end, if that's all right. I can't see your questions at the moment. If we go and look at the fault in that gap, right, the big strike slip fault, you can see it here. There are a number of right lateral displaced streams. It is very much an active fault zone. We can go out into the field. We can see exactly how active that fault is. We can dig pits into features that have been displaced by faulting, and we can determine how old those features are. Here is the fault. Here are offset rivers, offset alluvial fans associated with them. We know from our dating that these are about 80 to 120,000 years old. We can restore those river systems, alluvial fan systems, with 900 meters of displacement. That gives us a slip rate somewhere in that range. 9% also seems to give good agreement with rates of installed strain accumulation. And so this seems to be a very active, relatively fast moving fault, but no earthquakes. But when we look at the fault in detail, we see what appears to be a very fresh trace. These things almost look like the ruptures of an individual earthquake, right? Something that is still present in the landscape. As we walk along the fault, this is the fault going across here. We see a number, this is the fault line. We see a number of displaced streams, which seem to be of the order 6-7 meters, right? We see them extensively all the way along these 100-200 kilometer length of the fault. One thing that Nick Dodds has been doing is to take this WorldView 3 imagery, very high resolution, and to map all of the displacements that he can find along here. And he sees a peak of displacement somewhere about 6.6 meters. And we have also excavated a trench along the fault. We excavated it here where material is ponding against the fault scarp. And the results of that trench here, right, so this is just kind of showing you had an original land surface, the fault has displaced and down dropped this side. You have ponding in the against the fault scarp. And so these here are all the ponded materials from the available age control we have here. It seems as though the most recent rupture here was 500 to 700 years ago. So it was in the medieval, late medieval period. This is something that's actually escaped the historical record completely. A major earthquake missing from the historical record. Plugging in those values of length, of displacements, we get an estimate of moment magnitude somewhere about 7.8. And that's from the trench. We also see this earthquake, the scarp, displacing archaeological materials. So here we have the fault crossing a old agricultural landscape. And on that agricultural landscape, you can see a number of old field boundaries. And where those field boundaries cross the fault, we see that they are offset by amounts that we can actually measure from the satellite imageries. We went to this area here. We go into the field. This is the field boundary. All right, this is the offset. This is the fault. Again, it's about 7 meters. It's difficult to say exactly how old those agricultural landscapes are, but the suggestion is again that these things are medieval. And that's basically the end of the talk. I'm just leaving here with a picture of Ashgabat. We were saying that Ashgabat was heavily damaged by an earthquake in 1948, an earthquake that we are trying to work in collaboration with our colleagues from the National Academy of Science in Turkmenistan to understand better the source of that, as well as to look at the more widespread earthquake occurrence. We follow this pattern where we have a city that's increased in its population, and so this work again has an urgency attached to it. I thank you for your attention, and I believe now we're going to hand over to questions. So I'll stop sharing my screen, and thank you very much.
Yeah, thank you, Richard, for this nice overview of your works. We are about 100 participants now at the end of the talk, so I'm pretty sure there is people having questions. So I invite the participant to type on the chat if they have questions, and we're gonna use the next 10 minutes to to look at those.
I see two questions here.
Yeah.
So the first question is from Sheila Peacock. Thank you. Does modern microseismicity bear out your interpretations? In terms of which part? That one thing I would very much like to do actually is to look at the way in which some of these very large earthquakes of the last hundreds of years, obviously those ones that a lot of the examples I showed you, we actually know the sources of them, right? They were recorded at the time. We have some insights into their epicenters, etc. But those ones that go a little bit further back, and particularly ones like the Lepsi rupture in Kazakhstan, it would be very interesting to see how that is shown up in microseismicity and see whether we do see those patterns. And to be honest, I haven't looked because I don't really have full access to the data that would be able to let us do that. But it would be a really cool thing to be able to do that. I don't know if that answers your question fully, but this is something that's interesting. But yeah, it's also managing to get access to all of the data to be able to apply those things. I've got then another question from Ayush Joshi. How do we identify an ideal site to dig a trench in order to study a paleo earthquake? And for this, I would say that what you are looking for is a site where you have some stratigraphy, some sense of trapping of sediments, right? So that you will accumulate sediments. And from that, you will then be able to see a stratigraphy that will show displaced strata, those that predate the earthquake, and those that cap the earthquake. You're looking for relatively sheltered conditions, such that the sediments are fine-grained and do not, if you have big coarse cobbles, it's harder to make interpretations, harder to date them, to put that age control on. But often it's a matter of finding whatever is available to you in any particular place, right? The satellite remote sensing can be incredibly useful for paleoseismology because it allows you to survey the entire fault length beforehand, and you can hone down on those few places where you think you can actually likely get a decent answer. Then you go into the field and you can further narrow that down until you select those few that you will actually study, right? So again, this is actually quite a nice way in which you can get the remote sensing and the field studies that working very closely together. I have, if I take them in order, I got a question from the chat from Ahmad Hamad. Nice presentation. you describe active faults in seismology. Why not mention any information or case study from Pakistan? Well, I would love to. Sadly, I've never been to Pakistan. I would love to be able to undertake some of the investigations of the historical records or even prehistoric records from some of the major faults there. So yeah, I would love to in future. That would be wonderful. But you know, I haven't been everywhere yet. Now I will go to Rocco Malsavisi. How much slip is accommodated by off-fault deformation, i.e. not easily visible in the trenching? I think in that sense, it's always a big challenge. How much, if you're making measurements of offsets, how much of that is actually visible, and how much of that is going to be accommodated over wider zones that are really not visible at the scale of not easy to make measurements of. I think with the work that Nick was doing, that he showed for the Ashgabat or main Kopal-Darg fault, the approach of fitting lines to the streams and looking over some distance and then trying to estimate the offset from those, I think is hopefully gives you the best chance of catching the full displacement, or as close to the full displacement as you're likely to do. But of course, it's always a tricky thing, because we are taking measurements from a landscape that has had hundreds or sometimes thousands of years to degrade. So we're missing some of that fine scale detail that you can take if you have modern earthquakes. And again, this is kind of nice, because those examples from the modern period, we actually help us to understand what is likely to be occurring, and then we can try and take that further understanding and apply it to the imprecise record from history, right? So to at least be aware of it, even if we, and to take as many mitigation attempts as we can. I have another question from Chiu. Who says, I see the lowest peak on Nick's plot. Nick's plot is not the most prominent one. It's also the case in Wendy's area, I remember. Is there any particular explanation for that? Good question. I don't know, actually. Presumably what we are looking at is some sense of non-uniform creation of channels, right? You need to create these small channels in order to have them offset between each earthquake. And the question is, are these channels being formed randomly, on a year-by-year basis, or do we actually see the occasional century-scale flooding event that is putting those things in, right, and forming the channels that will then be offset by an earthquake? And if you're looking at recurrence intervals of earthquakes on the period, the 700 years, 800 years, whatever it might be, then you may be seeing different amounts of stream formation within individual earthquake cycles. I don't know if that's the real answer, but it's I think I see that as being plausible, but it might not be the full answer. Okay, one more. I can't see the full name of the person, I'm sorry to say, but the question is, very good presentation. Oh, thank you. You mentioned that the offset landforms in the Tien Shan have a very long retention time. So do you have the evidence or something to suggest that the Lepsi fault connected to the Dzhungarian fault during the last historical event, which ruptured the Lepsi fault? I would answer to that one, wait until you see what Wendy has been doing for her study, because she's been doing some really careful and wonderful mapping. And I think what you can see there is that these things may have been connected. But this is something that she's still working on. So ask Wendy and wait until her work is completed, and you will have a much better sense of how firm that conclusion could be. Right. So it's just a matter of sitting and waiting for a while. And then Jack Williams. Thank you for your talk. Two good questions. Do you assume the average surface displacement from geomorphology is the same as the average overall displacement in your magnitude estimates? Do you make a correction for slip being possibly? No, I have not done in those cases. No, and this is actually a very good point, that you know, we know that in large earthquakes that you don't necessarily have slip at the surface that is representative of the slip over the entire fault plane. So you might have peaks at depth which are not represented by that. However, what I've been doing is applying these relationships that have been built on measurements of surface offset or rupture length and magnitude. Right. So in some ways, if you take all of those earthquakes that you know have had those measurements made, and you build a relationship that associate those two sets of measurements, you get something that seems to scale. Right. The larger the magnitude, the larger the amount of slip, etc. And so I've just taken those scaling measurements and assumed that these earthquakes are follow those scaling relationships. So I haven't made any correction as such, because we don't have any information on whether these earthquakes had particularly high or low displacements at depth. There's a second question. Do the events that have both dextral and sinistral slip show a systematic relationship with fault orientation? This was our experience with the Kaikoura earthquake. Yes, they do. They are really systematic in terms of the orientation of the faults. You can use almost as a predictive tool to say what types of slip you will encounter when you look at the geomorphology of them in detail. So yeah, they do seem to. Oh, and we've had an answer from Wendy that, and it was from Haibo. Sorry, I couldn't read your name in your original question. So it does seem as though the Dzhungarian faults and the Lepsi fault could have ruptured together, although it might just be a part of the Dzhungarian fault, but not the entire length of the Dzhungarian fault. Okay, and thank you, Jack. I'm glad that answered your question. I think that's all of the questions so far.
Yeah, thanks. Yeah, thanks, Richard, for this this great talk and discussion under the difficult conditions. I think so. Stay tuned. We're gonna put online on our website the video, the record of this COMET webinar, and next very soon we're gonna announce the future COMET webinar. So stay tuned on Twitter and look our website to get more information in the future. And thanks everyone, and thanks Richard for this talk.
No, thank you to everyone.